guys, lesson 9.4. Today we're going to be talking about independent and dependent events. Let's start with vocabulary. This first vocabulary word states, two events are independent events if the occurrence of one event does not affect the likelihood that the other event will occur. So, for instance, independent events are two events that don't affect each other. I can roll a dice and roll a 1. That doesn't mean that it's going to affect the probability of me rolling a 3 later on. Now the next vocabulary word says two events are dependent events if the occurrence of one event does affect the likelihood that the other event will occur. For instance, if I have cards and I pull one card out, it will affect the probability of me pulling another card because now I have one less card in the deck. Okay, so that's an overview of our two vocabulary words for today. Independent events does not affect each other. Dependent events do affect each other. Let's talk about some examples. So in this case, we need to tell whether the events are independent or dependent, and we need to explain it. So the first event says, you flip heads on one coin and tails on another coin. So are these independent or dependent events? So the outcome of flipping one coin does not affect the outcome of flipping the other coin. Okay? If I take a coin and I flip heads, that doesn't mean the head just disappears. It's still on the coin. So it does not affect the ability for me to flip a tails on the next flip. It's still 50% for the heads and 50% for the tails. So the events are independent. But on this one, it says your teacher chooses one student to lead a group and then chooses another student to lead another group. In this case, if your teacher chooses one student and pulls them from the group, that affects the total probability of them picking another student. And the reason for this is that bottom number on your probability is total students. If you take one student away, that affects the total numbers that are available. So the teacher cannot pick the same student to lead both groups. So there are fewer students to choose from when the leader of the second group is chosen. So picking the first student does impact the probability of picking the second student. So the events are dependent. So basically the way I think of it is if your choice, your first pick, takes away from the possibilities of picking on the second time, then it's dependent because you're changing your total number. Okay, your turn. Tell whether the events are independent or dependent and explain why you picked that on your worksheet. Number 1, you spin a game spinner twice. First spin is blue and your second spin is yellow. So you have to ask yourself, okay, imagine I have a spinner, I spin blue. Does the blue come off the spinner? Well, no, the spinner stays the same. So since the spinner stays the same, my probability of spinning yellow doesn't change by me spinning blue and then yellow. So since they do not affect each other, our probability is independent. They don't affect each other, so they're independent events. Okay? Number 2, you and a friend are playing a game. You both randomly draw a playing piece, and you get to draw first. Your draw is a red piece. Your friend's draw is a blue piece. Are these independent events or dependent events? So think about this. You have a bag or some sort of thing, and you pull out a red piece. Do you put the red piece back? Well, no, it's a game. You're pulling a piece out and you're keeping it. Well, that changes the total pieces in the bag. So it changes that denominator for the probability of your friend. So that your draw does affect your friend's draw because it changes the total number of pieces he can draw from. So because of that, these events are dependent. One does affect the other. All right, let's go on. Now, there is a way you can calculate the probability of doing two independent events. Okay, so when you have two independent events, say I want to roll a 1 and then I want to roll a 6. What's the probability that I will roll a 1 and then roll a 6? Well, there's a formula for that. You take the probability of the first event and you multiply it by the probability of the second event. Simple. Okay, let's try an example. You flip 2 quarters. What is the probability that you will flip 2 heads? So there's 2 different methods, okay? Now the first one is going to show you how logic can do this. However, then I'll show you how the formula will make everything a lot simpler, okay? So the first method you could do is do a tree diagram. Let's map out. My first choice, I can pick heads or I can pick tails. Simple, okay? That's my first flip. But on my second flip, let's say I flipped heads. If I flipped heads, then my next could be a head as well, making one option being heads and then heads. Or my second flip could be tails, making my flip heads and then tails. So that's 2 options. Okay, what if I flipped tails first? Well, if I flipped tails first, my second flip could still be heads. So I could flip tails and then heads. Or my second flip could be tails. So that would give me tails and then tails. It asks, what's the probability of me flipping 2 heads? So all my options for 2 flips is heads, 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 tails, tails, heads, or tails, tails. Only one of those options is heads, heads. So the number of times 2 heads occur is only once out of 4 different possibilities. So my probability is 1/4. Now to do this method, you actually have to draw out the mapping diagram, and that takes time. Let me show you something that's a lot faster. What if we use the formula for independent variable? That is, we multiply the probability of the first event and multiply the probability of the second event. So the probability of getting heads on the first turn is 1/2, and the probability of getting heads is still 1/2 because they're independent, so they don't affect each other. So if you take 1/2 times 1/2, you get 1/4. And so the probability that you flip 2 heads is 1/4. So you can see here the formula is a much faster way of figuring out the probability of 2 events rather than having to map out a picture of the situation. Your turn. You roll a number cube twice. It says you can use the tree diagram to find the probability of the events. That is true. I am telling you, you don't have to, but if you would like to, that's fine. So all I'm asking you to do is, what is the probability of rolling a 5 and then a 3? Okay. If you got this right, your probability would have been 1 out of 36. I would still like you to listen to the explanation because I think it will help you. So if we were using the mapping diagram, we have the first roll and then the second roll. So total, we have, if we add up all these options at the bottom here, we have a total of 36 options. I can do 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Or I can do 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, and so on and so forth. So there's 36 options. I want to roll a 5, so I want a 5 first, and then I want to roll a 3. That is only one of my options. So I would have 1 out of 36. But watch. These are independent events. So rolling a 5 on a number cube, there's only 1 5 out of 6 different numbers, so it's 1 6. Rolling a 3 is also, there's only 1 3 on a dice that has 6 sides, so it's 1 6 as well. If you multiply those 2 probabilities, you still get 136. So your answer is 136, no matter which way you do it. Now you need to decide what will work best for you. However, I will tell you, using the formula will always be a lot faster than drawing out a diagram. Okay? So this is the probability of the first event times the probability of the second event. Okay? Let's go on. Now, Here, it's very similar, but it's a slightly different formula for finding the events of two dependent events. So you have to, when they're dependent, when one is affected by the other, you take the probability of the first event times the probability of the second event after the first event has already occurred. That means your total number on your denominator will change. Sometimes your numerator will change as well, but your bottom denominator will always change. So let's do an example. You randomly choose a flower from the vase to take home. Your friend randomly chooses another flower from the vase to take home. What is the probability that you choose a purple flower and your friend chooses a yellow flower? So, choosing a flower changes the number. So this is a dependent situation because once you pull a flower from the vase, it changes the total number of flowers in the vase. So it affects the probability for your friend picking a flower. So, for you to pick a purple flower, there are 7 purples and there are 28 total flowers. So your probability is 7 out of 28. Simplified is 1/4. Now your friend picking a yellow flower, there are 9 yellow flowers, but your denominator changed because you pulled a flower from the vase. Therefore, there aren't 28 flowers in the vase anymore. There's only 27. Therefore, the denominator is now 27, not 28. This is how many flowers are left in the vase. So your friend has the probability of 1/3. To find the total probability of you pulling purple and then your friend pulling yellow, we need to multiply them together. So 1/4 times 1/3 is 1/12. So the probability of choosing a purple flower and then a yellow flower is 1/12, or about 8%. Okay? We will have lots of time to practice this in class. So if you have a lot of questions, that's fine. Just let me know what they are. I'll be happy to answer them. But now you go ahead and try. During a card trick, your friend asks you to pick 2 cards. A deck of cards has 52 cards and is divided evenly into 4 suits: hearts, diamonds, clubs, and spades. All right, so that means if you divide 52 into 4 different, there are 13 hearts, 13 diamonds, 13 clubs, and 13 spades. What is the probability that the first pick is a heart and the second is a diamond? Okay, if we used our formula, we would do the probability of the first event. So what's the probability of me picking a heart? Well, 13 out of 52 cards. And then we're going to multiply it by the probability, Then we're going to multiply it by the probability of B after A occurred. So after the first event occurred. So we're going to multiply it by diamonds. We still have 13 diamonds because I pulled a heart at the beginning. Times 51 because I pulled a heart. So there's 1 card missing. Alright? Now all I have to do is multiply that. I can simplify diagonally. 13 goes into 52 4 times. So now my probability is 13 out of 204. So the probability is 13 out of 24, or about 6.4%. Okay? All right, that's all today's lesson. Please let me know if you have any questions, and we'll take time and practice this tomorrow or our next class.